Hey everyone, we're going to finish up class 5.2 together. I'm not going to do every single step with you, but at least get you most of the way there. So, depending on which class you were in, we left off somewhere here where we have the mass, we have the mass of a car going in a circle, the radius of the circle, and the centripetal acceleration. And we need to find the car's speed. So we decided to use the equation AC equals V squared over R because we have everything except for V. So working through this one, we plug in 3.2 for AC. V squared is our unknown over 45. The first thing I'm going to do is I'm going to multiply both sides by 45. So let me just get my calculator open. And I get 144. So now I have 144 equals V squared. Take the square root of both sides. You should recognize that. I get 12 equals V. So 12 meters per second is the speed this car is going around the track. So now we have to figure out what the magnitude of the centripetal force is. Now, I could have done this without the previous step. We have two equations for centripetal force. We could do m times AC or m times v squared over r, as we showed. So let's use the equation Fc equals m AC. M from our previous question is 1,500 kilograms. AC is 3.2 meters per second squared. Throwing that into our calculator, you should get 4,800 newtons. So what force provides the centripetal force needed for the car to travel around the curve? Like what is the agent of the centripetal force? Is it gravity? Is it tension? Is it friction? What is it? Well, think to yourself, if I'm driving on a road, and actually let's look at the picture up here, and I want to make this turn to go in a circular path. What would happen if I were to put a patch of ice right here? Would the car be able to turn properly? You've all experienced this, whether you've slipped on ice or been on a skating rink without skates on. It would be very hard, if not impossible, for the car to turn. Because what provides the centripetal force for a car going in a circle is the friction between the car tires and the road. So friction provides the centripetal force. So describe what happens to the magnitude of the centripetal force on the car as it travels around the curve if the speed of the car decreases. So we need an equation that relates centripetal force with speed. This is where that combined equation I showed you guys could be really useful. If I have the equation Fc equals mv squared over r, I could think to myself, what happens as v gets smaller? Notice that v is in the numerator. So if v were to get smaller, Fc would get smaller. So as v goes down, Fc goes down. Now, think about why that makes sense. If you're spinning an object around in a circle, like on a string, the faster you spin it around, the harder you have to hold on to the string, the more tension is in the string. If you swing it around slower, you don't feel as much tension. Now, what happens if the radius of the curve decreases? Well, if we look at our equation here, notice that Fc and r, that is an inverse relationship because r is in the denominator on the other side. So as the radius goes down, it's going to have the opposite effect on the centripetal force. The centripetal force goes up. That's why it's hard to turn a car in a very tight circle. So these are two old Regents questions. The magnitude of the centripetal force acting on an object traveling in a horizontal path will decrease if. So we have to think how all of these changes will affect the centripetal force. So let's see, Fc equals mv squared over r. So the radius of the path increases. If r goes up, Fc will go down. That is true. That's an inverse relationship. If mass increases, since that's in the numerator on the other side, Fc will also increase. So that is not true. The direction of motion is reversed. We've noticed the direction of v doesn't matter. and the speed of the object is increased. As we discussed earlier, if v gets bigger, Fc will get bigger as well. And I'll leave this last one here for you to finish on your own. Please show the work for this. Be careful here. It gives you the radius of the track as being 100 meters. All right, so please read that carefully. The next thing we're going to do is we're going to look at 5.3. Now, 5.3, this is the last thing we're going to do. You're going to turn this in. There are a lot of video links here, okay? You have a double period. I do expect you to watch these videos. There's a few questions on them, and the questions don't make that much sense if you don't watch all the videos, okay? They're all pretty short, and if you watch them on 1.5 speed, you can probably finish all the videos in about 10 or 15 minutes, all right? So we're going to discuss a little bit what a centrifuge is. You have discussed those before in probably your biology class. We're going to do some calculations here. We're going to talk about why Star Wars can be so inaccurate. In a lot of ways, we'll talk in terms of gravity in a little bit. So how do centrifuges work? So the clothes in a washing machine are forced into a circular path by the drum. If you ever looked inside your washing machine or seen it in action, there's a big drum that you put all your clothes into. They get wet, it spins them around. And then when it wants to drain, the holes open up and allow water to escape. The water is not forced into a circular path because it's allowed to seep through the holes in the drum and they fly off to the side. That's why the spin cycle is so important when you do your laundry. It actually is the first step in drying your clothing because it spins your clothes around really fast. So all the water basically gets pulled out of your clothing into the outside of the drum. Another thing we use centrifuges for is to separate mixtures by their weight or density. We'll just click here, by their density. That's how we separate cream from milk, lighter plasmas from heavier blood corpuscles. I don't really know much about that. And heavy elements are separated from lighter ones. If you watch these two videos here, these are about separating blood samples. They're both really good, especially the second one, the paper centrifuge one. And then answer, how do centrifuges separate mixtures like blood? Make sure you check out those two videos. All right, let's check out this video here. So watch the video or pause the video now, my video, watch this video, and then come back here. By the way, to click on these video links, all you have to do is open up the PDF version of the notes and just click on it there, and it'll open the link right up. So in this video, you saw an astronaut spinning around in like a training facility. So as the astronaut spins around, what's he feeling? Okay, he's feeling himself getting pushed into the seat. So he feels himself pushed into the back of his seat. So I think they mentioned in the video that the centrifuge has a radius of 18 meters. And if you looked carefully, you would have noticed that it spun around once every 5.5 seconds. So what we're going to do is we're going to find the tangential speed. Then we're going to find the centripetal acceleration that the person is undergoing. And then we'll use it to calculate how many G's this is. Now, calculating the number of G's is not a Regents topic, but I just think it's an interesting thing to discuss. So the first thing we have to do is find the tangential velocity, but we're not given a lot of information. We're given just two pieces of information. We're given the radius, and we're given the time. Okay, but specifically, this is the time for one revolution. So there's an equation that pops up in this unit. And what we have to do to find the tangential speed here is, since we don't have the centripetal acceleration or the centripetal force, we can use this equation. V equals d over t. Average speed equals distance over time. Now, this object is moving in a circle. So think for a moment, what's the distance around a circle called? We've done this before. This is the circumference. And the time it took to go around the circle was 5.5 seconds. Okay. Actually, I'm just not even going to put the time in yet. So again, speed is distance over time. If you go around a circle once in 5.5 seconds, the distance you traveled is the circumference, while the time is how long it took you to go around that one time. So let's throw this all into the equation. We have 2 pi 18 over 5.5. Just take a moment to calculate that. We have 20.6, we'll call it, meters per second. So that's our tangential speed, or just our speed if you want to call it that. The next one we have to find is the centripetal acceleration. AC equals v squared over r. That's only an equation to find it unless we have the centripetal force and the mass, which we don't. So the centripetal acceleration is equal to 20.6 squared over 18. So 20.6 times 20.6 divided by 18. And we get 23.6 meters per second squared. Now, how many G's is that? So this is a term you may have heard, like G-force, how many G's an astronaut experiences as they're taking off. Basically, how many times the force of gravity are they experiencing because of their acceleration? So that's why these centrifuges are used, as you saw in the video, in order to replicate that to the best of their ability. So how do you find out how many G's that is? You just divide this number, 23.6 meters per second squared, divided by 9.81 meters per second squared. That's 1 G. So 23.6 divided by 9.81, we get 2.4. So it's 2.4 G's. So how would the number of G's change if the centrifuge were spinning at a different speed? Well, we know that if the speed went higher, the number of G's would go up, right? Because the centripetal acceleration would go up. So V goes up, AC goes up, therefore G's go up. How does the radius affect it? Well, if the radius were bigger, the speed would go up, wouldn't it? Because R is in the numerator here. But if the radius were bigger, notice how AC would get smaller because the radius is on the bottom. So which one wins? That's a really good question, and actually one that we can answer at the bottom here. This is going to look complicated, but it's not too bad. So we have the equation V equals 2 pi R over T. And we have the equation that AC equals V squared over R. So what I'm going to do is I'm going to take V, plug it into V squared. So what I have is AC equals, this is going to look complicated for a minute, 2 pi R over T. That whole thing is squared because that is V, right? All over R. When I square the top, I get 4 pi squared R squared over T squared all over R. That simplifies quite a bit. Not quite a bit, just a little bit. This R cancels with this R. And what you get is 4 pi squared R over T squared equals AC. So that's not the answer to our question. So how is R going to affect the centripetal acceleration? Yes, if R goes up, the speed goes up. Therefore, the centripetal acceleration goes up. But if R goes up, the centripetal acceleration goes down, as we see here. So R must go down. This can be confusing. In this specific case, if r gets bigger, the centripetal acceleration is actually going to increase. And again, I know this can be confusing. So this is a unique scenario when we use this type of equation. This won't always happen. If you recall in the previous activity, you might be saying, well, why didn't it change there? Or which one of these would make the centripetal force decrease? For these ones here, there were no other variables that were changing. V was not related to R in those cases. So this could be a little confusing, okay? So this specific example we did in 5.3, you would never see something like this on the Regents exam, but I just want you to be aware of it, okay? So please don't let this confuse you. Generally on the Regents exam, you just look at the formula and compare the variables. This one was a little bit more complex. I just wanted to show it to you. But please don't get too caught up with this idea because this could lead to confusion, as I kind of just pointed out. All right, so you're not really going to see something like this one on the Regents exam. All right. So I just want to talk about this one, but you're going to do most of it on your own. So if you watch the video, so watch that really quickly. And after you watch the video, you should notice that the hub has a radius, they call it a hub, has a radius of about 5 meters. So it says to achieve a centripetal acceleration equivalent to the acceleration due to gravity on Earth, what should the period of rotation be? So you have to find tangential speed first. So you have two givens here. You have r is 5 meters, and you have AC has to be that of Earth, so 9.81 meters per second squared. So the first thing I want you to find is V, and then think about how you can find the period, the time to go around once. All right, so make sure you do that on your own. I'm not going to do that here for you. All right, so find V using AC equals V squared over R, then use the method, the 2 pi R over T, to find V. So just to talk a little bit about these, explain how a centrifuge can be used to create artificial gravity. Start with Newton's first law. This is exactly what we discussed in the previous class. So for starters, this is what I meant by why Star Wars is not accurate. In Star Wars, they walk on ships. They have no problem doing that. That would never happen in space because there's nothing pulling you down to the floor. So a lot of sci-fi movies like this one here, 2001: A Space Odyssey, they have centrifuges that people live on. It's also in the movie The Martian, they have it. They have centrifuges that create artificial gravity. So how does a centrifuge create artificial gravity? Well, the first thing is that objects want to move in straight lines. But the floor kind of gets in the way. They feel like they are getting pushed into the ground. Like gravity. That's what gravity does. It pushes us into the ground or pulls us into the ground. Here's a few videos here. This is a clip, this first one from Xenon Girl, the 21st Century, a Disney Channel original movie that you guys should watch if you ever get a chance. Anyway, it's a quick little clip of their ship. It's a big centrifuge, so they can stand up and walk around. Quick little thing about how they make atomic bombs, the Gravitron, which many of you have been on. That's a pretty cool video. And a little bit more from 2001: A Space Odyssey. So for this one here, what you need to do is almost identical to what you had to do up here. Okay, but this time I'm giving you the radius of 150 instead of 5, but it's still asking about how you can achieve centripetal acceleration like that on Earth. Make it 9.81 meters per second squared. So you're looking for V, and then you're looking for T. Again, to find V, that's real easy. AC equals V squared over R. Once you have V, 2 pi R over T, and you should be able to get T. All right, so that's everything. Make sure you watch these videos. They are really useful in just depicting this stuff. And this one here, I see can get a little bit confusing. So don't worry too much about this one. This one can definitely lead to some confusion. All right, just think about the variables in the basic form of the equation. AC equals V squared over R. All right, that's all for today. Make sure you get this submitted.